Good afternoon. So today we'll discuss mainly two characterization technique, that is small angle X-ray scattering and small angle neutron scattering, a little bit basics of microscopy. So in the next class we'll cover microscopy, so little bit microscopy I'll discuss. So first coming into small angle scattering techniques, so both SACs and SANs are related to small angle scattering, that's both related. If you see the scattering patterns, if you see in this structure, you can say X-ray neutrons measurement can't produce picture of particles. So that's why we are using here mainly scattering instead of microscopy for X-ray neutrons. So here if you see this diagram at the lower scale, you have about that about 10 angstroms, you have molecules, micelles, nanoparticle, zero point 0.1 angstrom, and so on. If you go, then this bacteria and all these things are very very small. So here the microscopic length scale, you have a molecules, nanocomposites, and a macroscopic length scale, you have grain boundaries, bacteria, which are quite large size. So if you see here that X-ray diffraction, that electron diffraction, those are mostly related to very few angstrom where the interatomic spacing we want to measure. So we go for this X-ray diffraction or electron diffraction. So, but here in optical, in the microscopy technique, you used to see larger size, like more than about 100 nanometer or beyond to 1 mm, that you can use with different optical microscope and microscope, or normal light scattering techniques like dynamic light scattering, static light scattering. Those will give larger size. But when you deal with particles of size of in the range of 100 nanometer or so, so in that case, like you have micelles, polymers, or some nanotubes, or some precipitate nanocomposites. So those proteins, so those type of structural information, size and shape, all those information can be obtained by these small angle techniques like small angle X-ray scattering or small angle neutron scattering. So by using this method, you can able to measure the size and say as well as shape, you can get shape informations. So if you see the scattering pattern, it's a very fast technique. In comparison to microscopy or scattering technique, is quite fast, and it gives in case of microscopy, if you go there, you used to see a particular small area information. So mainly you will get a local information, how the particles are arranged, how that area, how it's distributed. But in case of SANs or SACs, you will get quite global average instead of local information. You will get this type of scattering pattern, and from the scattering pattern you can get this type of 3D structures. So it can give you information about that the 3D information which normally you don't get other techniques, and it's an in situ during as well as it can do some non-destructive measurement using these scattering techniques. And the major disadvantage is that being it's global average instead of a local average, you have to interpretation of data. It's quite difficult. So you need to follow many models and to fit your data to find out that what is the information you want to get. So if a small angle scattering and microscopy you see, so microscopy uses lenses to resolve real space image of the sample. Like you have a sample here, the incident beam fall on the sample, and then you will get a image that is real space image on the after the focusing optics. You will get an image which is real space. But in case of small angle scattering measurements, it's mainly it's an interference of waves like incident beams, or light, or that X-rays or that neutrons beam. They will fall on the sample, and then it will scatter, and that you will get that wave generated from here after the scattering. So that you will see the interference of wave here. So then after the result, you have to convert it to Fourier transform. Then you will get a average over volume. Like the result which you will express here in case of scattering, it expressed over a particular volume. So you can use these small angle scattering techniques for characterizing your nanoparticles, proving interaction among molecules. If there are many molecules in a solution, so then how these molecules are interacting to each other. So those information you can get, or studying structure of cell assembly, like in micellar or in vesicles, those type of formation, so how they are forming by interacting with each other. So then this information you can able to get. And investigation of multi-component system, like you have a more than 3 components, you can able to identify them by using, like you can get more information about them by using small angle scattering technique. So here both neutron and X-ray scattering techniques are powerful tools to study mainly the structure as well as the dynamics of the system, that in material characterization over a wide range of length like 1 to 100 nanometer or a different time scale, you can able to see both structure as well as dynamic information. You can see that the neutron, the scattering mainly from nuclear interaction as well as magnetic interaction because of the presence of unpaired electrons. But X-ray scattering is from, scattering is mainly the nuclear interaction, while magnetic interaction is due to unpaired electrons. But in case of X-ray scattering, it is mainly from electrons. You can see this image. You have a X-ray. If you have an X-ray here, or you have a neutron here, you can see in X-ray mainly it can able to see the bone structure, can locate, but in case of neutron, you can able to locate low Z elements. So you will able to get information about both bone as well as leaf structure here. So both the leaves as well as bone structure, like that means the soft material, those information you can able to get by using neutron. So small angle scattering SHARCS mainly uses here, that uses X-rays with electromagnetic radiation, and that scattering intensity mainly depends on the electron density. You have a high Z material, your electron scattering is high as compared to a low Z material. But in case of this small angle neutron scattering, here you use neutron particle than X-rays, and here instead of there is no dependence on electron density, so it depends on the scattering length density, like how much neutron beam is scattering from a particular system. So that scattering length density mainly expressed in small angle neutrons scattering. So you go back to the history of small angle scattering, you will see around 1930 it was first introduced. Small angle scattering method was introduced by Guinier, and then 1838 to 1850 Guinier and others developed some small angle X-ray scattering fundamentals. So that they started initiation of the study, and then first experiment with protein was occurred in 1915. It's not that old technique. So in 1950, the first protein structure identified by small angle X-ray scattering. Then the use of small angle scattering increased with user-friendly, availability of different beam lines that helps us to increase the user-friendly. And see, in 1950, the publication in this research area is grows because in small angle X-ray scattering has achieved its momentum. So you can see here, so you can measure many parameters, like here you have intensity versus Q, that you have a vector, how the scattering is occurring in the particular vector. So you can see that you can measure the size of the scatterer as well as the amount, how much quantity of that element is present, and its polydispersity, distribution, scatterers, and shape of the scatterer, what is the spherical, cubic, rhombohedral. So those information you can able to get, and morphology also, and as well as composition, whether it is an anomaly, whether it is a composite. So those type of information you can able to get from the small angle scattering technique. So you see, if you have seen small angle X-ray techniques, so it uses mainly coherent elastic scattering of radiation at very small angle, like close to the beam. So that means if you have a sample here, incident beam is coming here, you can see here there is slight deviation of Q dash from the initial one. So that a small close to the state, incident is almost you can see here the scattered, it's almost close to the background, close to the straight line, straight through the beams. And whatever the incoherent scattering, that will give you background effect, whereas coherent scattering will give us elastic scattering of a radiation at small angles. So you can see here that K and K dash, K is the incident beam and K dash is the scattered one. So Q equal to K dash minus K. and of some is, and q equal to 2 pi 4 pi by lambda sine theta. So in this case, you can see that you can measure IQ with Q from 0.001 to 1 angstrom. You can see the vector is here and scattering from 1 to 100 nanometer. So you can get information about the size of the particles by using small angle neutron scattering and say or small angle X-ray scattering. So scattering experiment measure the number of neutrons and X-rays that scattered a different value of wavelength. Like your wave that Q vector, wave vector, that 4 pi by lambda sine theta. So it different of the wave vector, you can able to see how many number of neutrons or X-rays are scattering in that particular can say volume. So that will be expressed in that intensity will be measured, and then you can able to find out. So if you see here, this small angle X-ray scattering and diffraction, they are related to each other. So a factor K equal to 2 pi by lambda. You can say this is the incident beam, this is the K prime with the excited one, and then you can say that Q equal to this K star K. So that Q equal to 2K sine theta. If this is 90 degree and this is from theta, so Q equal to 2K sine theta you will able to get, and then that is nothing but 4 pi by lambda sine theta. And same in Bragg's law, what do you get? If you have a weak particle, then you have a n lambda equal to 2d sine theta. So you can rewrite this equation 1 by d, 1 d you can put left side and lambda can be right side. So 1 by d equal to 2 by lambda sine theta. So from these two equations, you are able to get Q equal to 2 pi by d. So the diffraction related to the scattering vector Q also. So you can see here from Bragg's law, the distance flow which inversely from distance flow Q is the distance is inversely proportional to the here the Q, that you can say Q equal to 2 pi by T. So from that you can see here, if a bigger distance, you need a smaller Q value. That you can see that this is the whole structure here, and there is a small portion here in red mark. You can see at high Q, that wide angle, when you go for wide angle, you can able to see the interparticle atomic level data of small structure. High Q means Q and D spacing are inverse proportional. High Q means that it's low D. At low D, this you can get information about interparticle interaction, atomic level data. Mainly you will get smaller structure, high theta Q value, you can get smaller structure. But when you go for low Q, you can see here the whole big information like small angle, that is interparticle, colloidal level data, and large structure. So you'll be able to see how interparticle, two particles are interacting, and what is the colloidal level of data. So those information you can get. So larger the structure, the smaller the scattering angle. You can see here in this image. So it's a big circle, is a small one. You can see the 2 theta here is scattering. You can see that larger is the structure, smaller is the angle. You can see here being a small size, your angle is large, but here being a large size. So you will get mainly information about the interparticular colloidal level data you will get. So you can see one example that 2 theta for various D value using copper K alpha. So you can see D 10 angstrom and corresponds 2 theta, and Q value you can find out that when you have a very small D spacing, your wave vector is stay higher, a little bit higher, and when you go to 1,000 10,000 angstrom at 1 micron D is bigger, so your Q wave vector is decreasing. So from this you can see at high angle X-ray scattering usual to theta when 10 to 160 degrees centigrade, you will able to see mainly the atomic structure. But in case of small angle, in this case small angle, you will able to see the big structure of like nanoparticles. Protein structure, particle size you can measure. You can see Q range is varied from 0.001 to 1 angstrom. So then in that case, lambda is 1 to 10 angstrom, and you will be able to get 2 theta equal to 0.1 to 10 degree. They're very small angle. At that small angle, we used to want to measure the scattering intensity. You see, both neutron and X-ray wavelength equivalent to the space between the atrium in crystal. Like the X-ray wavelength, that is neutron, where the X-ray wavelength, that X wavelength is equivalent to the interatomic spacing. So that's why, so mostly diffraction technique we use. That here we can do wide angle structure. So at less than 1 nanometer, we're able to get diffraction atomic structure by using this, wide angle XRD. But if you go to small angle XRD here, that you can get larger structure, 1 to 100 nanometer, like for give diffraction peak at higher wavelength corresponding to the atomic position of fibers, polymers, surfactants, liquids, biological material. Depending upon those materials, it gives diffraction peaks. So large structure scattered at small angle. If you have very, very big structure, so that means you go for a 100 nanometer particle size measurement. So you have a very small angle you have to show. So for techniques using small algae, huge material properties rather than atomic properties. So it gives the, like in case of when D is very, very low, that you are using the D spacing of that wide angle XRD. So D is very small. In that case, you are getting about information about the lattice and the atomic structure, those things. But when you go for very, very, small angle, that is small angle scattering technique, you'll be able to see the material properties rather than atomic properties. So you can see here in a SAXS instrument are conceptually simple, and it has a source that you have an X-ray generator or synchrotron, or you can use spallation source or reactor source for case of neutron, and as well as spallation. Spallation is also used for neutron source. So then that from the source that it has that neutron or X-ray beam falls on a monochromator or chopo, that would separate the particular wavelength it allow, and then collimated optics is there. The different angular divergence of the beam to the determines the maximum size fruit. So that then it go to the, you can see after the source, then monochromator, then it goes to collimator, and then it falls to the sample. Once it goes to the sample, then collects, detector comes into picture and collects the radiation scattered by the samples, and large detector provide better angular velocity. So the distance from the sample detector or wavelength determines the size range measured. Like you have to vary the distance far away, then you're not able to attain the particular measurement of the size. So if you see in case of SAXS experiment, small angle X-ray experiment, so once properly reduced and provides scattering cross section per unit volume. So after getting your measurement in case of small angle scattering technique, so you have to properly reduce it, and then you have to provide the scattering cross section. Here you can see intensity I0 is falling in the sample, and then di by d omega. So it will be Ti0 d epsilon by d omega. So from this equation, you can able to find out that di by d omega is the scattered intensity for particular solid angle. That particular solid angle, that is the scattered intensity, and I0 is the beam intensity, and T the transmission, whereas D the thickness of the material D, then D psi by dd equal to the scattering cross section per unit volume. So that the particular system, that is called scattering cross section per unit volume, is equal to D epsilon by D psi. So it's unit is centimeters inverse to straight inverse. So in SAXS instrument, more commonly provide loose data in absolute unit than a SAXS measurement. Like SAXS measurement, you have to reduce the data and you will get data not in absolute units. But here in case of SAXS instrument, more commonly provide the reduced data with absolute units, like mostly 1 by centimeter square. If you see the theory of small angle scattering techniques, both neutron as well as X-ray scattering. So you have an incoming wave vector scatter of electron cloud in case of X-rays. Like there is a electron cloud surrounding the nucleus. Then when you have an X-ray, that X-ray comes and then it's scattered of the electron clouds there. But in case of neutron, that is scattered from the nuclei. So you have a interference of scattered waves. At this interaction, you will see there is a scattered wavelets you will get, and that from that you will get all scattering intensity of individual scattered will added up, you will get a net scattering amplitude. So then you have to go for a Fourier transform of the structure, and then the scatter profile that can be described with the parameter of the scatter intensity. So how much the scatter profile, that depends on the material and how, and that it's the how much it's scattering is coming from that is called scattering intensity. If you see the scattering intensity is the magnitude IQ equal to square of the amplitude, that 1 by V rho r I omega IQ at dV, square of that. So IQ is modulated by the interference effect between the radiation scattered by different scattering bodies. So if a n number different scattering bodies and how they are scattering, so is modulated by the interference of IQ and these things. So if you have in a real space, you will see the particles are like this in the left side, have a smaller to bigger size. When you have a Fourier transform, in case of real space, you will get a scattering data. You can see IQ versus Q, all these things. When you have a real space, smaller size particle, you can see the IQ, that's the curve is not that much inclined to the x-axis, but when you have larger size, the q equal to pi by d, the distance, so you'll able to get large scale, length scale, you'll able to low q technique is this. So to characterize the size d, the d of the size of that this particle size d, one needs to do a scattering experiment in which q span in the range of the value q equal to pi by d, so that depending upon the scattering value, so you have to scattering experiment has to design here. So in general, that when you have a scattering intensity expression, you will see this is a sphere on which small angle X-ray scattering. Here you can see they are scattering at very low angle, almost parallel. Beams are coming and falling the sample. So here intensity, total intensity IQ equal to rho a number of the electron, number of density of the particle into rho p minus rho m, that is scattering length of the particle minus scattering length of the matrix here, then into p square PQ and SQ. So here the PQ, that is nothing but is a form factor which is interparticle structure factor, like within the particle how the structure factor varies, that PQ is equal to some square of FQ square, that is mainly called form factor. But PQ reflects the distribution of scattering materials in the scattering particle and depends on the shape and size of the particle. It also depends. But if you go to SQ factor, so that is nothing but interparticle interaction it gives. So this will be the structure factor, you can tell it. So SQ equal to in this equation you can find out, and related to the spatial distribution of the scattering and the particle in the surrounding medium such as solvent. So it's decided by the interaction between the particle and interparticle correlation distance. So that will define whether PQ or SQ, which one is dominant and in what case. So overall, that intensity is expressed in terms of form factor and structure factor. That is, form factor is interparticle structure factor, or this structure factor is interparticle, that is intraparticle form factor, interparticle is these things. So you can see here, if you go for a IQ equal to all these parameter, if you see, so this V square, PQ and SQ, if you remove, then it is IQ is proportional to mainly so rho P minus rho M per square. So that is rho particle minus rho medium square is equal to contrast factor. So how much intensity that you identify, that is the contrast factor here. So you can see hydrogen, lithium, oxygen, oxygen to cesium with cross-sectional Z value, cross-section of the X-rays and neutron. You can see that in case of electron, so it's from, if you have a large Z value, you have a quite bigger that scattering, that interaction varies. But in case of a nucleus, it's randomly varies. You can see that hydrogen is quite large and lithium is quite small, and then carbon, and then neutron scattering from the sulfur or manganese is quite low. So that's why X-ray, that in case of X-ray electron density, that this increases with Z value. So you have electron density dependence in case of small angle X-ray scattering. Whereas a small angle neutron scattering, you have a scattering length density dependence. So these both are very close related to provide complementary information, like from electron and neutron being complementary techniques. So you can able to get information accordingly both complementary information in these two cases. So if you see that electron density, as I told, it increases, increasing the Z value, but the scattering length density, that SLD, that depends, that is mainly that summation of Pi by V, that average scattering length density rho of the particle length density rho is simply the sum of the scattering length B per unit volume. So a particular unit volume, so how much neutron beam is scattering, so that is expressed in the summation of Pi by V will give you that scattering length density is called SLD. You can see this example. So you can see hydrogen, but it's surprisingly SLD is negative. So B, the 10 to the power minus 1, that unit, here you can see the scattering length density B into 10 to the power minus 12 centimeter. Here if you multiply that, hydrogen is negative where deuterium is positive. And similarly carbon and other, you can see how that B scattering length is varies. So as hydrogen and deuterium having different signs, one is positive, that hydrogen is negative, but deuterium is positive. So by you can manipulating the H by D ratio, you will simply change this ratio in the molecule, and it's in solvent one can vary the contrast. Like if a mixture, if you prepare hydrogen and deuterium, water and deuterated D2O, then you are able to varying that you can able to get a rho difference, that the constant, the solvent one can vary. So at zero contrast means no small angle scattering. So when in this equation, if you see, if you have this parameter IQ is proportional to mainly the contrast factor here, that is rho P minus rho M. So that or simply is the square of this is the contrast factor. If this is equal to 0, then you are not able to see any Newton scattering in case of here. So when this not 0, you'll able to see the scattering here. You can see here that how the contrast variation in case of sands. You can see, as you can see here, if you using this equation, that you can see if you want to see making how invisible to visible, like you have a core cell structure here, that you can see that pink and blue one. So if you want to see that that pink one or the that means core or the cell, so depending upon that one, you have to choose particular solvent that will contrast mix with that your element characteristic. You can see if you want to see the pink, then the blue has to be match with that solvent, contrast of that blue, so then you can able to see the pink. Similarly for the blue, you have to see the cell, you have to do the other things. So solvent matching, that is matching the scattering density of a molecule with the solvent. Like here solvent matching means the contrast matching means you have to match that scattering length density, you are matching that of the molecule with that of the solvent. So if the solvent has particular scattering length and your cell here, your cell is matched with that, then you are not able to see the cell, you will able to see only core. But in other way, if your this core is matching there with the solvent, then you are able to see the cell thickness. So here is that solvent matching facilitate the study of component by rendering another invisible. You have two things, so you are making one visible in presence of other. So simply in multi-component system, you can core cell structure, you can easily identify it from this type of by using contrast matching. So you can see here you have a glass rod here, and this glass rod is dipped inside this particular in water, and here also glass rod immersed in oil in right image. You can see if there is refractive index 0, delta Ri refractive index is 0, you're not able to see this glass rod here, but you can able to see the glass rod here. So that is simply that contrast matching del rho. If you see here in this case, del rho is 0, you can say, and here it's non-zero, that's you're able to see. So like optical contrast, so here in this case of small angle Newton scattering, to choose your solvent such a way that like hydrogen is negative and deuterium is positive. By varying these two, you can able to see one over the other structure. You can see here, like you have this type of structure when you can able to see row solvent, row core, and row cell. They are not equal. You can able to see you can see here that this type of you can able to see the solvent is here in green and core is in red and cell is here. You can able to see the big cell here. So here all the things you can able to visible. But in case of here, when you make the row solvent equal to row core, then you can see the core information is matching with that of the solvent, and you will able to see only this cell information. Similarly, that your cell is visible here. So here if core you want to visible, then you have to make row solvent of that of row cell, scattering length of solvent equivalent to scattering length of the cell. Then in that case, you're gonna able to see only the core information, cell is not visible. So by using these two parameters, n and number and v, since the volume, and you can able to get that pq and sq parameter, and you can see. So theoretically, that means if you see there is a calculating contrast matching point ax and by is the pure element, then you're going to do ax by equal to x into scattering length of dTO, the 1 minus 8 into scattering length of that water. So if you theoretically you can see by varying this 1 minus x and x, that varying that x, you can able to calculate that contrast matching point, and experimentally you can see here this is the that scattering distribution, that density versus wave factor Q. You can see with water 25 to water 50% here. This is the water in the top 50%, and we have a water 25% of the scattering is here. So you can, if you see that is calculate the square root of that intensity IQ with ratio of the water in water D2O mixture, then you can see, you can able to see the how that's IQ is varying with respect to the content of the water content in D2O mixture. At particular point here, it's crossing this. So if you see, so that contrast match is about 62% D2O and remaining water here, and 62% D2O, you're able to see that particular that solvent will match with that contrast. You can able to get the core or cell information like using this type of model. So if you see similarly, like a small angle X and neutron scattering and X-ray scattering, also you have a contrast variation, that del rho, that IQ is proportional to del rho square. So rho particle minus rho matrix. You can see here this here electron density of the particle minus density of the matrix. So by varying that electron density, you can able to see that contrast in case of small angle X-ray scattering. See here you can calculate that rho equal to number of E and E by N molecular weight and then density of the system. So number of atoms you can, so rho equal to, if you water that H2O, so you have a 10 divided by molecular weight 18.0152 into the density of this. You can calculate that rho of that electron density of that water. So you can see if your del rho is not equal to 0, you can able to see that the rho particle is rho matrix not equal to same, and you are not able to see in this image particularly. You can able to see here this type of structure. But if you are this pink color, you can see here in this image that rho is equal, del rho equal to 0 here in case of this particle and matrix. So whole that information will not get instantly, only you will get the information from this triangle information, that particular notch that I have shown here, that information you can get. But in case of electron density, the contrast is mainly caused here molecule composed of different atoms, like hydrocarbons in waters, or same molecules but different densities, like whether it's crystalline, amorphous region, or it is hydrocarbon in water. So varying the the molecule composed of the different atoms, so you can able to get that rho particle, rho matrix, that contrast can be differentiated. So the both information you will get from Sands and Sachs. So if you see the scattering density intensity equation, IQ equal to NV square. So your N is number of the particle, number density of the particle, the solvent, and V square is the volume of the particle, rho minus rho P minus rho M is the scattering length density, and that if you that I told, and PQ and SQ, PQ is form factor that depends on that will provide that depends on shape and size of the particle, whereas IQ is interparticle structure factor, so that is decided by the interaction between the particle and between the particles. Then you'll see here the information you will get that from N, that will give you number density, you will get in volume fraction, and from this you will also get information about composition, you will get from PQ factor, you will get shape, size, and how the size is distributed, and from interaction and the ordering you will get from interparticle structure factor SQ. So mainly the information that PQ and SQ are the two parameter here. So you can get both shape, size distribution from form factor PQ and interaction ordering from SQ. That information you will get. So if you see, if a dilute system, when there is interaction between the particle, here since this is the SQ is depends on the interparticle interaction, and if you have a dilute system, so SQ will almost negligible, you will get, mainly form factor PQ is dominance here. If a dilute system, so distance here is, that it's quite large, then the lambda, the IQ is proportional to the concentration. If you can see here, the intensity increases linearly if you increase the particle number in case of dilute system. So it will mainly PQ dominance you will see. But when you have a dense system, so that interparticle interaction come into picture. You can see large number of particles here. So there is an interparticle interaction. Because of that, so the SQ factor will be, comes into picture in the dense system. So you can also get the information like liquid crystal. From that, where you can see that there is a ordering of particular particles ordering here hexagonal lattice place. You can see. So because of this, there is an interparticle interaction between this. So interparticle interface cause structure factor SQ. So because of this, here, all they can interact with each other, and these particles, and you get structure factor dependence. But here if you see the dependence of scattering intensity on PQ and SQ. So as I told, PQ is simple shape and size effect will give, and SQ, that structure factor will give you interaction of the particles. You can see if you draw PQ or SQ versus that wave vector Q, you can see PQ is continuously decreasing, the blue one, whereas SQ, you are getting a peak and then there is a small oscillation. So here that IQ is mainly proportional to that is related to PQ and SQ term. So if a dilute system, in case of dilute system, as I told, that SQ factor will not dominate, only you will get PQ factor mainly. So here you will get this IQ is varies like this with respect to Q, and then you will get IQ is equal to 1 by R here. So in case of a concentrated system, you will get that SQ is dominant, so you'll get this peak here. You can see here this type of peak you are able to see. So when you have a 2 pi by dq, that you will get this type of this SQ dependence here and PQ dependence in case of dilute system, and SQ dependence in case of concentrated system that I told. So this form factors, that typically, if you see the scattering curves, it's the related information that I told, that if you do PQ versus Q, if you will plot log of Q or Q, you can see how this is changing that characteristic. You can see when there is a Q0 relationship here, we have a Q to the power -1 relation, we have a Q to the power -2 relation is there. So depending upon that, you can get information whether it is spherical, whether it is elongated, whether it is a disc cylindrical or disc shape. So these information you can be able to get both side shape as well as surface information. You can see here, if a Q to the power 0, that means you have a spherical shaped particles. You have a Q to the power -1 means you have a cylindrical shaped particles. So Q to the power -2, it follows the log of PQ. So how that this PQ is decreasing with respect to the Q vector, that you can see here. That if you fit it here, this region, if you do a fitting like this, so then that if Q to the power -2, you can say this is a disc shapes. So depending this, you have a low Q region, it follows that PQ equal to e to the power minus q square my rg square by 3. So you related to Gonnier model. Fourier model is in between that shape information. Then Fourier model, when you have a large q, you can see here the q to the power minus 4 or q to the power minus 3. Here you can see here large q region in this. So you'll give the surface information. So that this is the radius of gyration, cross-section structure, surface per volume. So all these information you can able to find out from small angle X-ray scattering by simply by fitting that PQ log of PQ to log of Q curve with Q to the power minus 0 or minus 1 or minus 2 or minus 3. Able to see all those information. So these are some example I have given that if you sphere case, as I told, it's called to q to the power 0, that first one here, q to the power minus 0 here. So here you can see it's almost going like this. So in this q to the power minus 1, that rod like micelles here, if you fit it here, it will go to q to the power minus 1. So rod like micelle, and q to the power minus 2 is a disc like or ellipsoid. You can get so different information and able to get by by fitting that q dependence of the PQ, you can able to get the shape information from small angle Newton scattering. So another terminology that you get from this small angle Newton scattering is that the pair correlation function analysis. So far what I told that you can get a shape information, and inside the shape information that you can also get a pair correlation function that is called PDDA, pair distance distribution functions. That is you can get that PR. From the PR you can find out that you can do a inverse Fourier transform, and then you can able to predict that whether it is this type of sphere shape or really cylindrical. So those information you can get. In addition to that, you get from this q to the power minus 1, minus 2 or to the minus 0 fitting what you got from the shape information. That also you can get from the paired correlation function. So this PR is nothing but the pair distance distribution function, which is inverse Fourier transform of the scattering function of the real space. So from the real space, you have an inverse Fourier transform. You do the transform, you will get pair distance distribution function, and that probability you can see here that PR is nothing but probability of finding a vector length R. So this is a vector of R length. So that R length can be how the probability of getting this in the whole scattering length. You can see the scattering center D max. So the maximum scattering length is this much. It is a protein interaction, protein molecule I have shown here. So this is a probability of finding this R, that is this length in the whole scattering vector. So that is the nothing but PR. You can able to find out. And then intensity. So if intensity is continuously decreasing, then you go for Fourier. If you Fourier transform, you will get this type of symmetric curve. So this here is the D max, the maximum that scattering length is here to here, and here is the probability of finding that particular R length R is maximum. So from that PR provides the real space interpretation of the IQ. So that from the Fourier transform you will get that PR, and then that PR, if you see the PR, it will function with respect to particle size. If you will R that scattering vector R with respect to PR you will plot, you can see you will get, if you in case of spherical red one, you can see we are getting a highly symmetrical curve. So that indicates a sphere shape. But in case of a cylindrical, you can see you are getting sharp and then monotonically decreases here in that case. But in case of a dumbbell, you can see here you are getting two peaks here, two PR correlation. One probability of finding this, another will be maybe this. So you'll get this type of structure. You have a core cell, how it's varying, and you have a disc like a broad symmetric pattern you are able to get in. So based on this PR distribution correlation function, so that you can get shape of the particles as similar to that you are getting q to the power minus 2, minus 1 or minus 3 fitting from PQ data. So if you have a small angle X-ray scattering data that both it may be a Newton scattering, or small angle X-ray scattering. Your analysis is quite difficult. So here the analysis, you have to choose a particular model. So once you choose a correct model, then you will able to get that particular that correct information. Otherwise, you will ended up with wrong information. So first, for the analysis, first you have to select a particular model for a possible structure interaction. So if there is a different interaction, and depending on the structure, you have a core cell model, or you have a cylindrical model, or so depending upon your possible structure, by assumption you have to take a selective model and feed the experimental data using the selected model. So you have to vary the physical parameter and fit it. If it fits, it's a good fit, then yes, it's possible model, and you can get a final model structure, and from the result, and you can complement that, find that what are the result you will get with other techniques. So if it's not good fit, then you have to again change the model. You have to keep on trying to get a better fitting. You can see here that how the fitting can be done, and if so you have a like this type of the intensity versus IQ flood. If you have a unimer plus micelle or rod like micelle, you can see how that scattering this is increasing here because of the rod like micelles, and then you have a mixture. So here this is how it varies, that depending upon the Q and Q minus 2, all this relation, you can able to see that how the scattering intensity is varying. And here this diagram, this mainly P85, and there is a poloxam or polymer that is increasing with different temperature. It's forming at 30 degree. It's a unimer structure. At 50 degree, we are able to getting a micelles plus unimer structure. At 75 degree, it's cylindrical micelle, it's forming. So from that you can able to get, since it's a micelle, you can see here it's almost here, it's very like -1 here, it -0 here. So at low scattering at lower angle, lower temperature is formed from the block copolymer dissolved as a unimer. So individual polymers are here, but scattering intensity increases with increasing the temperature, suggesting the self-assembly, that particles, the polymers are aggregating to form a particular assembled structures. Once the micelles are formed, their structure is a function of temperature. With increasing temperature, so large micelle, micelles will be large micelle will formed, so it goes to the cylindrical. So you can get this type of information, whether it is a cylindrical micelle, spherical micelle, or unimer micelle is not formed. So those information you can able to get by using small angle Newton scattering. So other information that the micelle also, like here that one is this, you can do the STS, sodium dodecyl sulfonate green one, and this is DTAP, dodecyl ammonium bromide, tertiary ammonium bromide. Then this is a C12E10 the micelles. So you can see here, so by fitting you can able to find out whether it is a spherical micelle or is the elliptical micelle. So you can see the semi-major axis and minor axis, and what is the aggregation, how much is the aggregation of this, and polydispersity, or all those parameters. By fitting you can able to get all this. So the fitting of those software and all these things that I will not discuss, but by using different model you can able to get all this information of a micelle structure. Like say elongated micelles, so you can able to see that whether it is a semi-major axis, minor axis, so both you can able to get, as well as then polydispersed, how the particles size distribution you can get. And also you can, like similarly you can see you have a F3O4 nanoparticle here, so that is dispersed in water and DTO mixture. So on the F3O4 particle you have a water, and all this is conjugated, so you can able to get that using SACS data. SACS data, you can see the SACS data will give you the particle size of the ferrite, the core particle. You can able to get the SACS from the small angle X-ray scattering, whereas the particle size or the thickness, both either cell, what is the water molecule surrounding, and the thickness core, all those in surfactant coating information you can able to get from the SANS experiment. So whatever the size you can get from dynamic light scattering DLS, that is RH 10 to the 10.5 nanometer, so that you can compare with your core and core plus cell. You can see that about for 8 about that variation is quite small at 10.5. Here you are getting a 8.8 nanometer from SANS data. So by fitting that the SANS data, you can able to see the both information of the core as well as cell information, since SANS is both, that both this core as well as cell, both information you can get from the SANS. So here is another example that if you go for SANS study, you can see this is a CTAC and that's both SANS and SACS analysis, Newton scattering, the left one, so right one is the here, this one is the X-ray scattering here. You can see in case of SANS getting a one peak symmetric peak here, but in case of SACS we are getting one peak here and there is another peak here. But when you the same C tag instead of C tag, if you go for C tag, such as ammonium bromide, in case of chloride, you could take bromide, you can see the SANS is still that symmetric one, but in case of SACS, you are getting two peaks and second both peaks are well reserved here. So that is because that when you go for this chlorine here and it's bromine here, these two, that SACS is that is more sensitive to the electron density, that the electron densities of the head group, like the sulfur head group here is chlorine, and that there is bromine is here. So if you see bromine, the electron density is quite large. So because of high electron density, you can see there's a two that two in case of SACS, you have a two fix here. Here only chlorine case you can able to see there is only one half is here. So if you see that the SANS signal can assess the contrast between the solvent and the hydrocarbon chain in the micelles, like the hydrocarbon chain that is there as well as that bromine and chlorine. So that contrast it can measure that using. In case of SANS, only hydrocarbon chain is possible, but in case of SACS are sensitive to inner structure of the polar shell because of electron density of the head groups, counter ions, and penetrated slot. Those things is there, so you can able to calculate, get the information for the head as well as from the tail that this hydrocarbon chain. So the contrast variation obtained by SANS and SACS prove the difference between the nuclear atom and the electron density respectively. Like you can get that nucleus of the atom, from that you can able to get that SANS information you will get, but in case of SACS, the both information you will able to get that electron density as well as the nucleus of the atom. So, so both core cells type structure or is the micellar information, so those can be possible. But for the neutron scattering the studies, you need a reactor facility, whereas small angle X-ray technique can just get a X-ray machine you can do that quite easily, but big facility like reactor you have to use for small angle neutron scatterings. So this is a Dhruva reactor that I have shown of the present in BRC. So you can see here in that photograph, you can see you have a here from here that neutron beam is generating and coming to the sample here. So then it goes to the detector. You have a beam stopper here. That linear beam it will stop, and there are the scattered beam you will get here that will go to the detector, and you're able to see that information about the structural information of the shape, size, those information you can get. The common parameter that wavelength average that we are using in case of Dhruva is 4 to 10 angstrom, and then the Q range is mainly possible 0.015 to 0.5 angstrom. And so if anyone from outside BRC they want to do small angle neutron scattering, so they can contact the SANS facility at BRC for these measurements. So we'll just take 2 to 3 minute breaks, and then so we'll go for the other topic that on optical and electron microscopes here. So you may so far that the neutron and X-ray scattering technique I have discussed. So in the next class we will mainly study that electron microscope. So we'll just little bit will the introduction I'll give today's little bit about optical and electron microscopes. So we'll wait for 3 minutes and then we'll continue the lectures. तो लाइव है अभी, it's live.
अभी शेयर करो फिर से। ब्रेक हुआ था क्या?
ब्रेक हुआ था एक्चुअली।
एक मिनट, कुछ यूट्यूब पे कुछ है क्या?
Okay, so now we will discuss second part, that is optical and electron microscope. So if you see that mostly that structure determines the properties of a material. If you see what is the structure of that material, so that explains what is the characteristic of that particular material. So to identify the structure, you need most of these microscopic technique. If you see for the crystal structure, all this information you can get from X-ray diffraction analysis, like structure determination. But if you see, they go little larger from you can see 10 to the power minus 9 to 10 nanometer, in that range. If you see the TEM, SEM, and optical microscope come into picture. So here you will be able to see the both grain boundary, grain, pores, all those information or components, so that or fracture mechanics. So this type of both mesoscopic information and microscopic information, as well as atomic microscopic information you can able to get from TEM, from an ACM little bit, and for optical microscope you can get mesoscopic or microscopic information. So you have a both basic to applied research in all these things. These microscope techniques are widely used. So if you see the microscope, it came from a Greek word that is called micron, that means small, and scopos, in other words, to look. So from these two words, the terminology microscope came into picture, and it is an instrument of viewing an object that are too small, and the science of investigating small object using such an instrument is called microscopy. That means you are seeing a small object by enlarging it through, and the way of investigating with the small object by using a microscope, which is called microscopy. So in microscope, you can divide into two types. First, simple microscope, another is compound microscope. The simple microscope means you have a light microscope, that's mainly optical microscope. You have phase contrast microscope, you have fluorescent microscope, you can use dark field or bright field microscope. So these are mostly light microscope. In case of compound microscope, they are divided into two, that light microscope and electron microscope. In electron microscope, these are mainly majorly used, that scanning electron microscope, transmission electron microscope, and a confocal microscope. So these are electron microscope that commonly used. So we will mainly discuss that scanning and transmission electron microscope, and a little bit about optical microscope. So in the microscope, you see different terminologies like magnification, that means the degree of enlargement or enhancement. It depends on the focal length of the object, magnifying power of the eyepiece. So means how the degree of enhancement, that is called magnification. Then you have a resolution. The resolution is ability to resolve, two adjacent images, to see that how well you can resolve those two images, or two structural information you can get by using the ability that is called resolution. The resolving ability, you can simply say. And then you have a limit resolution, the minimum distance between two visible objects at which they can be separated and non-contact to each other. If there is a two objects are contact to each other, so in the minimum limit resolution, that how you can minimum distance that two can be visible. So that will mainly LR depends on 0.61 by wavelength of that light by numerical aperture. So here, similarly, numerical aperture is the ratio of diameter of lenses to its focal length. So based on the diameter is the focal length, that n is equal to n sine theta by 2, where n is diffractive index and theta is the angle of aperture here. You can see theta by 2 here, depending upon that ratio of the diameter of the lens to its focal length. That's called numerical aperture. Then another terminology comes here is walking distance. That walking distance means distance between the front surface of the object, front surface of the lens to the surface of the object. You can see here, this is the left image here, the sample specimen is here and your microscope is here. You can see this is that walking distance is here. In this case, this is walking distance is here. So this distance between that front surface to the lens, surface for the lens to the object, so that is walking distance. By varying the walking distance, you can you can focus or defocus, you can get that image easily. So if you see a conventional microscope, that simple lens microscope, that means you have an object plane, then you have a convex lens, and then you have image. If you have object here, then you can put a convex lens here, and then you have a like normal optical microscope. It will be fall in a particular point, and then you will get a image. Here you can get a image in this case of conventional microscope. That in that case you will get mainly you have an image here, and you are getting an inverted image here. That the inverted image you will get, and u and v relation, that 1 by u, that is the object to the lens distance, that the u and v the object to the image distance v, then what you will get 1 by u plus 1 by v is equal to 1 by f. So you'll be able to see this relation first. So here magnification is equal nothing but v by u. And you will get is a normal conventional microscope. So the image you will get, if you see the scenic photography image, that you have object here, and you will get a object very small focal length object you will able to see here. In case of photography, you will able to see an opposite image at a certain distance, the focal point. So in eyeglasses, you will see the same almost similar size image, but it's inverted here. But in microscope, what you are seeing, that this is the object here, and you will get an inverted image at a quite large big one. So that's it. In the microscope, the main thing to see the small object at a large size. So if you see the optical microscope, the instrumentation part, so you have an illumination source, that is a light source or lamp. So radiation source, and here that and the condenser lens is there to focus the beam after this light source, and there's a condenser lens. So light will come here, and it will be using the condenser lens, it will be focused to the sample specimen beam. Here is the specimen here. So you have a sample set situated between the illumination and image system. This is here, and then you have an objective lens here, and then it comes the imaging part here. So imaging part consisting of an objective lens to focus the beam. What are the beam transmitted through the sample, you'll be able to see, and through the objective lens, will focus by the objective lens, and then form an intermediate image here. And this is the intermediate image you will be able to see here, and that intermediate image again go through an eyepiece here, projector lens, so that the projector lens will magnify the portion. This image will magnify, and you'll be able to get intermediate at the final image here you will be able to get. So here then is the image recording system that convert the radiation into a permanent image you get. So mainly 4 stages: illumination stage, and then sampling stage, then imaging stage, and finally you will get a recording that image recording system. So you are using mainly condenser, objective lens, as well as projector lens in case of optical microscope. Here you can see, you can vary this focus, there's objective for there's 10x, 20x, or 40x, so you can that objective lenses you can change, and through this eyepiece you can able to easily see the specimen here. So but you can see here that for optical imaging you need image has to be perfectly prepared, like sample preparation is little bit required. So that first of all you have to polish it to make the flat sample finish, as optical microscopes have to low depth, like field of depth optical microscope, the penetration of light is the depth of this field of view is less in case of optical microscope. So that's why you have to be, sample has to be flat and it has to be optically finished. And then you have to etch to reveal the chemical details. Like this is, you can see, this is the brass image here. This one is a brass, so chemical etching, this is a stainless steel, and this is a new deformed niobium. So chemical etching removes the material from the surface at different rate depending upon the orientation and composition of the phase. So by using chemical etching, so the top surface or some specific information you can get by removing that, whatever the dentate structure, whatever the rough morphology that can be removed, and you can be able to get whether how these grains are distributed in case of stainless steel brand. You can see the grain boundary here. You can see the deformed, how the structure is deformed in case of niobium. So those information you can able to get. You can see the optical micro image of the bronze that's revealing a cast dendritic structure. This is the bronze image, and this is how the dendritic structure has grown inside this bronze that you can able to see by using optical microscope by mirror finishing this. You can grown on the substrate, you can this biological structure that grown on the surface. So those information you can able to see by the optical microscope, or you can see the alloy system. You can see this is one type of alloy, this another type of structure. So this type of alloy information, so you can able to get by using optical microscope. But the optical microscope you not reveal. So it's very small object, you can't able to see it by optical microscope. So for that you need an electron microscope. So electron has much shorter wavelength than that of visible light. If you see visible light, the wavelength is 200 to 400 to 800 nanometer, but the wavelength of the electron is very less. In case of this TM is 0.025 0025 nanometer, so it's quite low. So electron wavelength is being very small, and this allows the electron microscope to produce very high resolution image than the standard microscope. Like if you have a standard microscope being is a wavelength is quite large, and that to in electron microscope the wavelength is very small. So because of that, you can see lambda for electron is 0.002 to 0.1 nanometer depending upon the energy. As I told, in case of TM, it's 0.0025 nanometer if you go for a 200 keV TM microscope. So if you see that this electron microscope, its electrons have strongest interaction with matter. So any radiation, so many types of information can be available. And so the interaction between electron and the matter is very high rather than in comparison to light. So you'll get much more information, and it is high intensity, high energy beams of electrons are relatively easy to generate. Like you can able to generate that high intensity by thermonic emission, because using that other like systems like thermonic emission, like FUG, field emission gone, so can able to create a high intense beam with high energy, so that can generate easily, and it is used in conjugation with variety of ancillary techniques. Like this electron microscope can combine with other technique, so you'll get more information, and this can be thin sectioning is possible. Immunolabeling, you can do negative staining, you can do like some antibody, those type of you can conjugate immunolabeling, and to answer specific question you can able to get conjugating different variety of ancillary technique. You will get more information. Like for a microscope like SCM, you can use EDAX analysis, chemical composition analysis. In TM, you can do EDAX analysis, or energy electron energy loss yield spectroscopy analysis. So you can get more information from electron microscope. That's why electron microscope, which is more widely used for to see the smaller object like both SCM and it's like scanning electron microscope, and then you have a transmission electron microscope. You see these slides I have already discussed that all microscope technique based on that interaction volume, that this is the interaction volume here. So how the electron beam interact with the specimen. So depending upon that, different this microscopic techniques are used. When electron beam strikes on the sample, a large number of signals generated. It may be electrical electron signal, it may be photon signal, both way can be generated. If an incident beam, so in the interacting, as I told you, that there is a possibility of backscatter electron, so that there is a possibility second electron, that electron can absorb, it can generate another electron, that secondary electron, both backscattered and secondary electron are used in case of scanning electron microscope. So these are the two bases of that scanning electron microscope. So you can use either backscattered or secondary electron form. And in the same time that X-rays are maybe produced due to interaction of electron with the matter, so you can use that X-ray is produced, so that X-ray can be mapped by using that EDS facility, energy dispersion spectroscopy, that EDAX or EDS. So you can able to this way SEM or TF. So you can use that elemental mapping. You can see whether they from copper with K alpha, nickel K alpha. You can element analysis, and as well as it's up to certain extent your quantification can be done in case of using this X-ray mappings. Or if there is an Auger electron generated, so that Auger electrons can be used for Auger electron spectroscopy that will discuss later. If that electron is transmitted through the matter, so you can get a transmitted electron. So the transmitted electron you will able to get used in the transmission electron microscope to see the shape, size of the smaller object of the size of 10 to 100 nanometer or much lower than that. So if there is possibilities that there is a inelastic scattering or elastic scattering is here. So depending upon that, you can able to get more information whether how this electron beam is interacting with the matter, that energy, electron energy loss spectroscopy that we will discuss. So yield spectroscopy will generate will give you more information like X-ray. We studied EXAPS and EXNES, like electric that here say similarly electron energy loss spectroscopy. You can get those in type of information from that transmission electron microscope. There is possibility of cathodoluminescence. So what is the electrical signal that can be generated? So that can also use for some other techniques. So overall, if you see the whole electron microscope based on the interaction of an electron beam with that of matter and generation of with either secondary electron or tertiary electron or transmission of the electron. So most of these microscopic techniques based on that. So in today's lecture, so we covered small angle scattering techniques like small angle neutron scattering techniques, small angle X-ray scattering techniques. So those most nanoparticles, proteins, so those size, interparticle interaction, the size of the particle. So those information we can able to get from that small angle, X-ray or neutron scattering. Where in the wide angle X-ray scattering, as I told, you can get the lattice parameter, the crystal structure information. However, if you go to the larger structure, if you want to see, you have to go for a very, very small angle that 2 to 10 degree in that small angle, but you will see the larger structure mostly scattered at small angle, so that the small angle that q depending on the q vector. So you will able to see that large structure information by using the small angle neutron scattering. You can see the form factor, that interparticle interaction, or that will give you interparticle interaction. You can get shape and size information, SQ factor and PQ factor, form factor, when able to see the other information. So you will able to both that particle information, interparticle interaction, then the size of the particles. So both information you can calculate from the SANS and SACS data. Being they are complementary to each other, both SANS and SACS. So you'll get some both complementary information. For example, I shown that CTAC and CTAB. So how that SACS can be used to get the information of both head as well as hydrocarbon tail group. In case of SANS, you can get only information about that hydrocarbon chain. So the SAX, mainly small angle X-ray scattering, provide information about the mesoscopic length scale, that is 1 to 100 nanometer in that region, whereas small angle scattering data analysis application depend on diverse set of approximation model. The analysis part of the scattering technique is quite difficult than diffraction or microscopic techniques. So you need various model, you have to choose particular model to analyze it, and then by once you get a proper model, you will able to see the core at the cell information. You can able to see the micelles, cylindrical, spherical micelles, those information you will get. It's neutron, that I told neutron is mainly interact with the nucleus, and X-rays will interact with the electron. So because of this, you will get complementary information between X-ray and neutrons. And also in addition to that, we'll study a little bit about microscopic techniques, especially optical microscope. So how the optical microscope produce images, and then this electron, why you need an electron microscope, that mainly that due to very smaller wavelength, you can get a very smaller size, you can able to measure by using electron microscope. And these all microscopic technique based on the interaction of the particle, interaction of the electron beam with your matter, with your particle, that interaction volume from where it is either produce backscatter electron or secondary electron, that used in case of scanning electron microscope, or it transmits electron, that will be used for the transmission electron microscopes. So in the next class, we will study mainly that transmission electron microscope and scanning electron microscopes. These two we'll cover in next class. So if there is any question, so you can raise now, or you can even email me later on also. Since there is no question, so we'll stop here. We'll meet on Thursday for the next lecture.